to the next lecture about petitRADTRANS by Eleonora Alei Evert. So please feel free to share the screen. And I remember you that you can continue the discussion in the Slack channel.
All right. Okay, I'm gonna share quickly the link to the collab. Should be the right one. All right. So if you want to follow along in this lecture about petitRADTRANS, first thing I have to tell you is to make a copy of this collab link of this collab repository, and you do it by clicking on File and then saving a copy on your drive. And that allows you to mess however you like with the code with this notebook without messing up the whole general notebook. And I actually did that already because I needed to get ahead of the game. So before we start talking, I suggest you run this cell here because it's gonna take a while. I did this for you already, so I can just go on with the introduction. All right, so we have studied so far, we've seen so far much of the theory, and now we're going to have a deeper look at one of the models that actually allow you to produce low and high resolution forward models and as well retrievals. That kind of sits very well in the topic of today's session. And I'm gonna start with the introduction about petitRADTRANS, and Evert is gonna continue on talking about retrievals. Everything that you'll see here, well, most of it is taken from the documentation, and I put a few links to the petitRADTRANS documentation to help you study more in detail a few topics. And this link actually opens up the documentation of petitRADTRANS, which is full of everything you might want to know about that. And if you want to ask questions about the technical side, obviously Paul Molière is the guy that created the whole thing, but also if you don't know who else to ask, also Evert and I can give you a hand since we collaborate within the group. Right. I'm gonna leave you, most likely I'm gonna leave you a few of the exercises that we've prepared for you to your own time so that you can just play with it, and then we can discuss the results in the Slack channel petitRADTRANS. And yeah, all done. Right, so we are ready for the installation. And maybe, well, let me go on this one. Maybe you have already run this cell without really knowing what you're doing, but now I'm going to tell you very quickly. So what we are going to do in this cell is to download multi-nest because it's going to be used for the retrieval section. And here is a quick fix, and I'm pretty sure we at least encountered multi-nest and pi-multi-nest in yesterday's lectures. And this is the fix that we found in a way, this row here, to link the library so that we can actually use pi-multi-nest within Google Colab. Otherwise, you don't really need to use this if you're running it locally. So once we downloaded multi-nest and compiled it, and then we're going to install pi-multi-nest. And then this is the part that takes a longer time. We're going to download the opacity data. This is a great set of folders that I've prepared for you for this particular lecture, because the actual one, the default one, is much larger, is gigabytes and gigabytes of absorption lines, and we would not have had as much time to download it all. So suggestions, if you want to do exercises or if you want to use petitRADTRANS, you should go and take the actual input data folder, and actually you can find the link to it. Where is it? Here, yes, the installation docs in this link here. And you can also add your own opacities and you can follow a tutorial that tells you exactly how to do it. Right, so we have downloaded this folder and unpacked it, and you'll find it here in the input data folder, and it collects all of the abundance files, the opacities, and everything that petitRADTRANS needs to do the calculation. Then we can install petitRADTRANS as both, in this case, we are using, you can install petitRADTRANS with the pip installation, but for the purpose of this lecture, we're also downloading the beta version from the GitHub repository. It's okay. You can find everything you need to install it locally in the installation docs. Right, so let's assume that this was run already, and let's get started. So the first thing that you need to do when starting to use petitRADTRANS is to import the libraries that we need for our lecture, and these are the general libraries that you need to plot and show, very basic. And the petitRADTRANS related libraries are these ones. So this is how you import the RADTRANS class, the constants, the natural constants that petitRADTRANS comes with, and the retrieval classes. Make sure that you link the input data path to where your data is. So in this case, we are linking it to the folder that we just downloaded. So we make sure that petitRADTRANS can read the opacities when it needs to, and that they are looking good. So let me just do it. It's going to take a bit. Right, we have run this, and we are also using the PRT petitRADTRANS plotting style. Okay, so once this is done, we can start working with petitRADTRANS. The very first thing that we need to do is to define a RADTRANS object, which is the class that we are going to use, and that has all of the, yes, exactly, Evert. If you're installing it yourself, you can add the input data path to the bash profile in case you're using it, and that allows you to just have it forever and ever and just call petitRADTRANS with no issues whatsoever. Anyway, importing the RADTRANS class allows us to create this object that's the model that we're going to use. And in this case, we are starting with a very simple atmosphere, just including sodium between 0.5 and 0.6 micron. And we do it like this. So we create the RADTRANS object, and these are the arguments that it gets. The line species requires an array of strings, a list of strings, and you can include all of the species that you're gonna use. In this very simple case, we're just including sodium. And then we need to specify the borders of our calculations. That is up to where we want to calculate the spectrum. In this case, from 0.5 to 0.6 micron, which is very small. Right, if we just write things this way, petitRADTRANS is automatically going to use the low resolution setup, the low resolution mode. And basically what we do in low resolution is use the K-correlated opacity lines. I'm not sure you're familiar with the correlated K. Here you can find more information, but I'm briefly gonna pull it up. And as you see here, basically what happens is that when you want to model an atmosphere, you are generally dealing with a set of different pressures and temperatures, right? And needless to say, a huge bunch of wavelength points. This can be really heavy from the computational side, and because in the end of the day, when you're going to calculate the radiative transfer, and this is probably going to be treated in a more detail in the next session, what you're doing is basically comparing point by point every single line, every single wavelength. and every single opacity of that wavelength. What the correlated K approach does is sorting out a single bin of wavelength. As let's say we take into account a single bin of wavelength, and then we sort out in an increasing order the opacities, so that we go from this band that we have here to this line here, which has by definition the exact same integral, because we're just resorting the lines from the smaller one to the larger one. And then the advantage of it is that it's a smooth function, and that allows you to basically fit this line with a series of points, which is much lower than the original sum of points that you have originally. So at the end of the day, what you do is you reduce by massively the amount of data that you need to store, but the downside is that you inevitably lose some information on the resolution and how exactly the lines are, where the location of the lines is exactly. You can do it, you can somewhat save it by just picking up very small wavelength bits, but you need to in a way trade off with the amount of data that you're going to store. Anyway, this is the difference. You can have more information about this by looking at this or other sources as well. Sorry, not here. But we can also work with the high resolution line by line mode with petitRADTRANS. We just have to specify the mode, LBL. That's the keyword for the mode that we're going to use. And I can run this as well. It's going to take a little longer because it's going to load up more data, but it will be fine. See, just still a couple of seconds. If you notice here, the name of the lines is fairly different. The keyword for the lines is fairly different, despite it being in both cases sodium. This is a little bit tricky because the keywords in petitRADTRANS are very specific because they stand for different line lists or broadening treatments or any sort of variation. In general, the best practice is to just click on this link. It would pull up the documentation and have all the links or all the references to the various included line species and all the details about the broadening factors, the provenance, and all of that. Anyway, in this case, we don't really care much about it, but we want to create something that's a little bit more complicated to show the potential of petitRADTRANS. In this case, I'm running this cell and I'm creating a RADTRANS object that includes water using the high temp database, CO using the high temp database, CH4, CO2, and nitrogen, sodium and potassium. And we are also including Rayleigh scattering for hydrogen and helium, and continuum opacities with hydrogen and helium. So collision-induced absorptions for hydrogen and hydrogen-helium collisions. And we are using a wavelength range that goes from 0.3 to 15 microns. So this is a little bit different. Right. This is what we're going to use for the remainder of this lecture. But we will come back to the previous ones shortly afterwards. So once we have defined the object, now we need to define the pressure temperature profile, which is essential if one wants to calculate the relative transfer. So first thing to do is to define the pressure array. And we define it by using a long linear spacing of 100 points going from 10 to the minus 6 to 10 to 10 to the 2 bars. And then we are assigning this opacity structure, this pressure structure to the atmosphere object. Here we need to do a remark Every unit in petitRADTRANS is in CGS except for pressure, which is in bars. So you may want to remember that. It's a little bit unconventional at times, but make sure that you use everything in CGS. Right. Once we define the pressure, we can then create the temperature profile. And what petitRADTRANS requires is to have a temperature profile that has exactly the same shape as the pressure profile. So in this case, the pressure is an array of 100 elements. So we want to have a temperature array of 100 elements. Ideally, one would have the values of the temperature at each determined pressure level. So for the purpose of this lecture, I created a function, and I've taken into account a few common temperature profiles just to see what changes. But again, this is totally not mandatory. This is just useful for the purposes of the interactive plots that we're gonna see. Sorry, Evert, I'm gonna read it. I read the comment.
Sorry, I'm just making comments in the chat. You don't need to worry about it.
Okay, no, because I just see the notifications, you know. Okay, cool. Right. So the profiles that we included so far is the isothermal profile, the Guillot profile, and the polynomial profile. These are commonly used profiles that really that could be useful or not depending on your situation. The isothermal profile is obviously just a constant temperature profile with respect to pressure. The Guillot profile follows this complicated equation and is generally used for Jovian planets. And here I'm not going to go into the details of every parameter that it requires. Just make sure that let's just notice that gamma is the ratio between the optical and infrared opacities, and that's what in a way determines if the profile is gonna have an inversion or not. And then we got a polynomial function, which could be used in some cases. What we do here in this function is we require the user to provide a keyword to decide which case are we using. And if it is isothermal, what we do is we fill up an array of points that has the same shape as the pressure array, and for which every temperature is the same. And we require, in this case, the parameter for the temperature that we want to have. In the case of the Guillot, here we have a very convenient thing, is that the Guillot profile is already included in petitRADTRANS by simply querying it, calling up the module of the natural constants. Here we are shortening it up to label it NC, and just call it by Guillot global, and it needs the pressures, the kappa, infrared, the gamma, gravity, T and T equilibrium. And we have given some of the default profile just to see what happens. And then I've created a polynomial array, and this is basically done with the polyval function that comes with NumPy. And it takes as input the coefficients, and in this case, this is the default parameters that I've given. And the more coefficients you give, the higher the order of the polynomial. This is not relevant for you, but just in case you want to play with it at a later stage, increasing the number of coefficients, feel free to do so. So to create the profiles, we just create the isothermal, Guillot, and polynomial by giving the appropriate parameters, and then we plot. And let's see what happens. Right. This is the three profiles that we've used so far. So as you see, we have different, in a PT plot, we have the same pressure array and different temperatures for each profile. This will be used later when we are going to use the, we're going to see what's the impact of the PT profile in, for instance, the transmission or the emission spectrum. Right, this is another step done. What we need to do next, is to define the chemical composition. We need to know what the atmosphere is made of. And here, petitRADTRANS, another warning point, we're using mass fractions instead of volume mixing ratios. And you can convert between one and the other by using this this equation here, but there is a new in the latest update. We can petitRADTRANS kind of helps you to do it, and you can convert between mass and number fraction by using this function as well. Right, so I'm creating here as well another function, not at all necessary for the purposes of petitRADTRANS, but just for the purpose of this lecture. And if you don't want to use functions at all, you can refer back to the documentation there. Everything is written without taking the functions into account. What this function does is super easy. It takes the temperature array as input and creates a dictionary of arrays, one per each molecule or each species that we are including in the atmosphere. Warning here, we need to make sure that whatever we included when defining the RADTRANS object is in the mass fraction element. Otherwise, it will go, petitRADTRANS would not compute because it won't find the abundance that is required from the RADTRANS object. In this case, we just use the uniform distribution for each species. And as you see here, we're just multiplying it, a number by the shape, making sure that it has the shape of the temperature array and of the pressure array. So at the end of the day, all of the pressures, the temperatures, and the mass fraction, they all need to have the same shape. And what else we do? We just calculate the mean molecular weight similarly, and then we return it. So I'm calling the function, but just giving it whatever temperature array. I don't really care about the values of the temperature, but just the shape of the temperature. Temperature array. So I'm creating the mass fractions and then I'm plotting, and let's see. Oh, it was run already, sorry. And this is what we get, super easy. This is like this is the abundance of this mock planet that we are using. As you've seen so far, we are using very simplified profiles, very simplified temperature profiles and compositions, but since petitRADTRANS only needs to have arrays of the same shape, you can potentially even read from a file. And this could be useful when coupling petitRADTRANS to other models that create that work with the radiative transfer or that calculate the abundances of an atmosphere. So you can have altitude dependent or pressure dependent profiles. No worries about that at all. Another important thing that could be useful to some of you is that also petitRADTRANS can help you define the abundances that go best with some PT profiles, and this is done by using the Poorman equation in the that's included already in the petitRADTRANS code, and you can know more about this if you click on this link. Right, now we have defined the whole RADTRANS object. We defined everything that we need to start actually calculating spectra. Let's start with the transmission spectrum. Well, I kind of lied up to so far because we just missed a few more parameters that we need to determine the transmission spectrum. And in particular, we need the radius of the planet. And as you see here, I'm declaring a planet that has 1.382 Jupiter radii. This is very convenient because it in the not constants, the natural constants module that comes with petitRADTRANS, you can find a bunch of constants that are already in CGS, so you don't need to worry about anything. So make sure to check it out by clicking on this link. Then we have to define the gravity of the planet in CGS, of course, and the gravity, this gravity should correspond to a specific pressure in the atmosphere. In this case, we are using the pressure of 0.01 bars. In this case, we are excluding clouds. I wanted to mention that because clouds mess everything up by a lot, and this will be clearer in the next session. But if you want to include clouds, go check out the documentation again. Right, so to produce the spectrum, the transmission spectrum, is actually pretty easy. We just need to call the function that's defined in the RADTRANS object, and we need to provide the temperature, the mass fractions, the gravity, the mean molecular weight, the radius, and the pressure of reference of the gravity. And then if we plot it, here we go. I'm plotting it again just to make sure. Right, this is the transmission spectrum that we see. So we see the transit radius with respect to wavelength. So we come now to the first interactive exercise. I fear that we won't be able to do all of them during this talk because of lack of time, but make sure if you want to play around with it, try to answer these questions and make sure to type on Slack what you find out, because it may be interesting for everybody. So what we do here is defining another function that's again totally not mandatory, but again I like functions, so I do them. And what we do is just recapping whatever we did so far. So we define the pressure, and so we define the pressure array, and we attach it to the atmosphere RADTRANS object. Then we define the temperature profile. In this case, we're picking up the isothermal profile, but you can change it if you want. Make sure just to change the parameters as well. Otherwise, it will go use the default ones. Then we could we are defining the abundances and the mean molecular weight by using this function. These are obviously the functions that I just conveniently created a few minutes ago. And then we are declaring the radius and the pressure, and then we are keeping the gravity as a user provided value. So we can calculate the spectrum, and then we're plotting it. This is a neat snippet that just allows us to save the old runs so that we can compare all of them. And this allows us to have an interactive widget that works by simply clicking on Run Interact. What's doing it is just executing this function here, and then you see exactly the same spectrum as before because we are using the default values. But let's see. Let's change the temperature, for instance, and see what happens. Something should happen, right? This is the second spectrum. That's the spectrum at a higher temperature, and you feel free to vary the values of these three parameters and see what happens, and try to find an explanation for it, and we can discuss it a bit better on Slack afterwards. Right, I'm gonna move on because the clock is ticking, and then we're going to do the second bit, is the emission spectrum. So we're just changing the geometry of the system, but petitRADTRANS can perform equally as well. We just changed the function that we're calling. So keeping in mind everything that we've declared so far, the RADTRANS object, the PT profile, and the abundances, we just have to run this function to produce a spectrum. And this function requires the temperature profile. In this case, I'm using the Guillot, the mass fraction array, and the gravity and the mean molecular weight. And then we plot, and this is what we get as a result. This is the planet flux in CGS units with respect to the wavelengths in microns. Right. Here we are excluding the scattering from the surface and the scattering from the atmosphere itself, the thermal scattering. But this can be indeed included in petitRADTRANS, and you can add it and work with it if you need to by clicking on this link here. Right, another exercise. So we have very quickly gone through the emission function, and we can do similar thing by defining a function that collects the various that defines the things that we want, that we need to detect an emission spectrum, to create an emission spectrum. So again, we define the pressure, we give up, we assign the pressure to the atmosphere object, the RADTRANS object, we define the PT profile, and in this case, I'm going to allow you to change the type of profile that we're going to create and see what changes when producing a different emission spectrum. Then we're defining the mass fractions and the mean molecular weight. We're declaring the radius, and then calculating the flux by using calc flux as we did previously. And then again, this is just the widget, and that the storing of the previous the previous spectrum. Right, so let's run this. Right. See, this is basically what we had before, because I'm using the default values. But what happens if we change it to the polynomial, for instance, by using the default and using the default values? This is another emission spectrum. What happens if you change it to the isothermal? I don't know. I'm not going to do it. You're going to show me on Slack. And you can try and answer these questions as well. Right. Finally, are there questions up to this moment? Because before we move on to something slightly different, it might be a good time to answer some questions, if there are any.
Not now.
Cool. All right, I'm moving on so that I'm leaving the floor to Evert, and it is more complicated bit. Right, so if you remember previously, we defined two other objects, the high resolution and the low resolution, and we may be interested in finding out what's the difference between them and finding it, seeing it directly. So what I do here, this is nothing else than a recap exercise that allows us to define also to see the differences between the line by line and the K-correlated. So again, same approach, defining the pressure array and then assigning it to both the atmosphere line by line and the atmosphere K-correlated RADTRANS objects, then defining the variables that we need, and then defining, in this case, I'm defining the temperature profile, because I don't want to use the functions anymore, just to show you that it works exactly the same, even without the functions that I just written. So I'm defining the profiles, and then I'm calling the Guillot global function in the constant module. And then I'm creating the abundances, and then I am producing the transmission spectrum. Right, so in this case here, check out, I'm adding even more abundances. But if you keep in mind, we didn't really have H2 or helium in the RADTRANS object. What it will happen is that petitRADTRANS will simply not read these two, because it's not the file, the species that it was queried for. But here, I'm adding actually twice the sodium, because it actually has two different keywords, one for the line by line, one for the correlated. And obviously what's going to happen here is that the line by line is going to read it only the species that it can read. So the keyword that it's allowed to read. And likewise, the K-correlated object is going to do that. So in principle, you can have a massive abundance dictionary. It's not going to mess with petitRADTRANS, but just pay attention to it. In this case, the differences would not be, there will be no difference at all, because in this case, I'm purposely just using the same abundance for both the sodium lines, because I want to compare what would happen by considering the same amount of sodium, just by changing the line by line or the K-correlated approach. And then I'm plotting it. And this is what should happen. That's important. Right. So here we are seeing the transit radius of the same objects, the same planet, because it has the same pretty profile and same abundances, but at different resolutions. So depending on what you need to do for your work, you may be interested in seeing the sodium feature rather than not. And it really depends on you, but petitRADTRANS just works just as well. Right, so this would have been the end of my part, and Evert is going to continue using the same exact collab, but I'm gonna stop sharing in the meantime.
And I will take over here. All right. Everybody can see my screen? I've lost the zoom there.
Yes. Yes.
All right. So yeah. So Eleonora, thank you for going over how petitRADTRANS works, and especially for explaining how to kind of go from just having your physical model, that's your chemistry and your PT profile, and converting that into a spectrum. So as we've seen throughout all of the lectures up to this point, a lot of the task we have here in exoplanet science is kind of going from some data set that's going to be your transmission spectra or your emission spectra, or whatever it is that you happen to have, and then coming up with kind of a statistical view of what the actual planet properties are. So yesterday we saw kind of how to do that using a grid model search with species. And today we're going to go into how to actually run the retrievals that have been talked about in many of the other talks. So as I said, there's a few things that we need to be able to do this. The first off is your data. So for us, we're going to be using a simulated data set of an HST transmission spectrum. You need an atmospheric model that will describe your chemistry and dynamics and radiative transfer throughout your atmosphere. So that's basically what Eleonora just explained. And we need a sampler. So we're going to be using PyMultiNest that we installed way up at the top of the collab. We also have UltraNest that you can use, and you've seen other people use MC, and things like that, which we don't have built in right now. But whatever it is, you need some way of kind of exploring the larger parameter space of your planets. And this is, so then a little bit of background on the statistics that has kind of been given before already. We're essentially taking Bayes' theorem and computing the evidence for a given model and trying to see how well this model fits and what is the probability distribution or the posterior probability distribution of all of your parameters of interest. And this is the measurement that we really want to get out. So the first thing we really need to do is set up what kind of model do we want here. And this, of course, is going to depend on what type of planet you're looking at. If you're looking at a hot Jupiter, your model is going to be very different than if you're looking at a terrestrial Earth-like planet. So deciding what temperature regime and what PT profile is appropriate, whether assuming a hydrogen-helium envelope is appropriate, even understanding what the signal to noise of your data is and understanding how many parameters you can add to your model. All of this factors into what you want to put into your model. And of course, the more complicated you make your model, the longer it's going to take to run, but hopefully the better physics you will actually be able to incorporate in it, or the more freedom you will have to make measurements. Hopefully, if you have many, many parameters, you have very excellent data to be able to constrain them well. For us, with only HST data, which is really only a few data points, we really want a pretty simple model here. We're going to be using an isothermal model. We're going to throw in a cloud, and we're only going to use water and methane, together with hydrogen and helium, of course, to come up with our model atmosphere. In practice, actually writing a model function to run in petitRADTRANS has a few rather strict requirements, and we'll see how the function is actually set up here. But the general idea of it is essentially exactly the same as what Eleonora did above. And so I'm just going to walk through and actually write the function here. In the collab that got shared around, this is already completed, but I'm just going to fill it in so that I can explain as I go. So you're going to start out just by importing the petitRADTRANS retrieval packages, and we're going to start writing our model function. So a model function in petitRADTRANS to run in a retrieval takes 4 parameters. You have your radtrans object, which is the same as defined above. We have a dictionary of parameter objects. So there is a parameter class in petitRADTRANS that has, and each parameter has a name, and it has a flag whether it is a fixed or free parameter in your retrieval. It has a prior function associated with it if it is a free parameter, and it has a numerical value. And so for all of the parameters that you include in your model, they have to be in this dictionary to be passed through. And then these other parameters we don't really care about right now. This just returns your pressure temperature profile rather than a spectrum. And petitRADTRANS has an adaptive mesh that you can use for the pressure grid. We don't care about that right now. We don't need that. So what we do want is to make that nice model. The isothermal, and we're going to use free chemistry, so just the vertically constant abundance is same as above. So we need to get the pressure array from that petitRADTRANS object that gets passed into the function. So here is where there's that bit of a hang up in that when you input a pressure into petitRADTRANS, it has to be in bar, but internally it's in CGS, so we just divide by this factor of 10 to the 6 here. And then we're going to want to define the rest of our parameters. So the first thing we want is our temperatures. And to get the value of any of the parameters, you have to go to the parameter dictionary that gets passed to the function, together with a keyword temperature, I can't spell, that is associated with this parameter. So the parameters that you give to the retrieval and the parameters in the model need to match here. And then to get the numerical value, you just take the value. And as with everything else, this becomes an array with the same shape as the pressure array so that it can vary as a function of pressure. All right. So the next thing we want is to take care of the chemistry. So in this case, we're going to have that isothermal chemistry. So we want that same mass fraction dictionary that Eleonora described above. I'm just going to call it abundances here because I know that's what I've already called it below. So if you know exactly what species you've passed into your retrieval, you could just fill out this dictionary something like this. You give it your species name that matches your species name in your parameters, and you multiply it to get the full array. So you could do this with every species that you have in your dictionary, and then just go through and fill it out with the values that will get sampled in the retrieval. We're going to be a little more general when we write this function here, and because the actual names of these parameters can change depending on what you set as your resolutions for both your data and your model. And it makes it a little easier if you ever want to change what chemistry you have. So I'm just going to copy this in. And instead of going through one by one, we'll just loop over all of the species that are associated with your RADTRANS object and fill it out automatically by the matching parameter with the correct name. We also want to make sure that we are getting the total mass of all of these species so that we can end up calculating the mean molecular weight. Actually, I don't think it's needed for that. It's just needed here for when we take care of the hydrogen and helium, which is just the remainder of the atmosphere. We're assuming a mostly hydrogen-dominated atmosphere, 76% by mass, minus whatever little bit is everything else, likewise with helium. Then we finally need the mean molecular weight, which we have a nice function that does this for us. And we throw it all in and calculate. In this case, it's going to be a transmission spectrum, so we use the calc transmission function. And you just pass it all of the values that we put in together with the log g. We have log g, but we want the actual gravity, so we take the exponent of that. And we have cloud pressure, we have radius. This p0 bar is the radius of the planet where RPL is defined. So depending on your type of planet, this can you might want to change what this is set to. Usually though, this 0.01 bar works well. And finally, your RADTRANS object, after you've done this, you'll need both the wavelengths, whereas the RADTRANS object gives you the frequency, so we just convert it to wavelengths in micron rather than in centimeters. That's where this factor of 10 to the minus 4. And we need the spectrum. So to do that, we get the transmission radius of the planet, but then we want to divide it by the radius of the star and square it so that we have the standard depth, transit depth. And we want to return both this wavelength and your spectrum. So this is our entire model. This does the bulk of the actual work in the retrieval. So once we have this, we essentially just wrap it up in a nice, pretty format, and it will get run through the sampler millions of times, and you will end up with your posteriors. So how do we go about setting up the rest of the retrieval now? First off, are there any questions about the model we're using or how you would set up a different model of your choice? Anything?
Nope, not yet.
All right. Again, anybody feel free to just interrupt if you have questions. This should be hopefully a bit interactive since we're just trying to figure out how to actually run this, and hopefully people will find it useful. So in petitRADTRANS, we've got a couple classes to actually set up and run the retrieval. And the first that we care about is the retrieval config class. So this stores everything that you need to describe your data, describes all the parameters you use, and just is the kind of base of what your retrieval will look like. And there's the full details in the documentation. There's a tutorial there to run this. But you set up the class basically like this. You want to give it a name, hopefully something nice and useful so that you'll be able to remember what you did, though there is a summary file at the end that stores most of the things that you would need to know that. You can set the run mode, so either you set it to retrieval, which will run the full sampler and it will compute everything, or if you already have a finished retrieval, you can set this to evaluate, and then it'll only worry about reading in the existing files and making plots. Oh no, that's not good. All right, I hope multinest is still there and I don't need to re-download everything. It looks okay. So then the remaining two parameters, you have the adaptive mesh for the pressure grid. Again, we're not going to worry about that. And scattering. As Eleonora said, for the emission spectra, you can use cloud scattering. This makes things a bit slower, but more accurate. We're doing transmission spectrum. We don't care. The next thing we want to do is actually import the data. So we have a file that's already given for this data. And this can either be a text file, a CSV, you can load a FITS file. There's a few caveats on how everything needs to be structured, but again, that's all explained in the actual documentation. For adding the data, you give it a name associated with the data, you give it the path to the file, and you associate that function that we wrote above. We do this because in principle, if you want, every different data set that you use can take a different model. And you would want to use this, for example, if you were combining low resolution and high resolution data. Or if you were doing, say, the east and west limbs of a high quality transit spectra. Essentially, whatever you want to do, this would give you a means to use different models for different data sets, but combine them in the full retrieval. You can set the opacity mode, whether you want the correlated K opacities or the line-by-line opacities, and then you can set both the data and the model resolutions. So the data resolution will just convolve your, it's a little misleadingly named, it is really your instrumental resolution, and it will convolve your model to the instrumental resolution. The model resolution, however, sets the actual resolution of the opacity tables. So we use, for the correlated K, there's a nice package called Exo-K, and we can use that to bin down the correlated K opacities to a lower resolution so everything just runs faster. If you use the line-by-line method, it will just downsample the high resolution line-by-line opacities to whatever your resolution is, though we don't really recommend doing this. If you downsample your line-by-line opacities, you need to be at a much lower resolution than your data needs to be at a much lower resolution still than what your model is. This isn't as much of a problem for the correlated K opacities. All right, so we've now read in a data file, we've set what our resolutions are, and we can start to add in all of those parameters that we gave to the model. And so to add a parameter, we just use the add parameter function. So again, every parameter has a name associated with it, so our star, a flag, whether it's a free parameter in the retrieval and you want the full posterior distribution, or false if it's a fixed parameter and you know the value. So in this case, we know the value of the star. We can set exactly what that stellar radius is in this retrieval. And we can do this for the remainder of the parameters. So we can take the gravity. Let's say we know it here because we're going to want to actually plot some spectra here before running a retrieval. Planet radius. And then let's say for the temperature, we want to actually have this be a free parameter. So here you can see that we've set it to a free parameter, but now we have this argument to the function here, and this defines what the prior associated with the function is. So maybe you wanted a Gaussian prior. In this case, we wanted a uniform prior that will go from 300 Kelvin to 2300 Kelvin. So this should cover the range of interest for this particular planet. Choosing your priors is important if you want to make sure that you have physical bounds, but you want them to be fairly general so that you're actually sampling the full space and not going to be running into the prior bounds. And finally, let's throw in a cloud here because clouds are cool. And this just says the base cloud base pressure, so to go from 10 to the minus 6 bar up to 2 bar, or 10 to the 2 bar, sorry. All right, then finally let's set what actual opacities we want, so the Rayleigh species and the collisionally induced opacity species, exactly as above, and what line species we want to choose. Here with the setLine_species function, you can also tell it whether your model is an equilibrium chemistry model or a free chemistry model. In this case, it's free chemistry. And you set what you want as your prior boundaries on this. So we want to go from a mass fraction abundance of 10 to the minus 6 all the way up to 0. It's set up in the same way as these functions here. We also have an extra function that just lets you list all of the species that you happen to have installed on your system. This would just tell you what you actually have available to use. All right, so can run that, hopefully. I think I need to run several of these by now. Random capacities. And now we've got a little setup here to actually play around with how the retrieval is really going to work. So let's just set up an atmosphere exactly like Eleonora did. And if everything works properly here, we'll have a nice little interactive plot with sliders so that you can go into this notebook and play around and just adjust the temperature, the cloud pressure, and the abundances of the species to see how does this actually change the spectra that I'm going to get out. And this is a wiggle. And see, so if we increase the temperature, so in blue we have our data, and in red we have our model, and it calculates what the log likelihood is. So this is effectively running the retrieval, but by hand. We can move the clouds around, and you can see that that makes a huge difference to the spectra. So we can put the clouds way deep down. You can adjust the water and methane abundances, and clearly all of these have significant impacts on your spectra. So I highly recommend going in and just playing around and seeing how close can you actually fit the data here. How do these parameters actually impact your model, and in particular, how can they be degenerate? That's a big thing that you're going to need to worry about, especially because the retrieval won't know beforehand whether these parameters will be degenerate or not. Hopefully that will come up in the corner plots, but it's important to know how your parameters actually behave. So hopefully everybody has the notebook and that works, and you can all play around with that. But now we want to actually run the retrieval and get out the posterior distributions rather than doing it by hand, because doing it by hand would be very, very slow. So we're going to just reset the parameter dictionary so that we can turn all of these into free parameters in the retrieval rather than having them fixed like we needed to just to make that plot. And finally, we want to just beforehand set up a bit of the plot so that petitRADTRANS can generate them automatically. So this section here just tells you what parameters you actually want to include in the corner plot, because if you have a 30 parameter model, a 30 parameter corner plot is really hard to actually look at. So we want to just restrict it to a few parameters that we're interested in. And we only have 6 parameters or something, so it's fine. And then most of these have nice defaults in petitRADTRANS, but it just allows you to set things like the axes labels and scale them, whether you want it linear or log scale. And if you want to do things like plot multiple instances of your models as sampled from your posterior distributions, you can tell it how many times you want to do that if you want to generate plots like that. And finally, this is an important parameter here, which just when you plot the pressure temperature profile, it needs to know which data set you want to look at. Here we only have one data set, so it has to be this one. Ideally, all of your data sets will end up using the same pressure temperature profile unless you have a good reason not to. So once we're through that, we've set up the entire retrieval configuration. And that then gets passed to the actual retrieval class, which basically takes it and runs it through the PyMultiNest or UltraNest sampler.
Sorry, there is one question.
Yeah.
By Viviana. How do you define an interesting parameter in your case? Wouldn't you want to see all the parameters in general to be sure it worked?
Absolutely, yes. Yes. But sometimes I'm only interested in, say, a couple of the chemistry species because I have a retrieval finished and I only want to see those ones, and I have the pressure temperature profile, and so I don't need to see the 6 parameters after I've seen them once. So it's more of just so that you can make nice plots that you want to include in, I don't know, a presentation or something. But yes, you should absolutely be looking at all of your parameters after every retrieval. Yes, should clarify that. All right, running the retrieval. So we now have the actual retrieval class that takes in the run definition that we set up, the retrieval config. You give it an output directory just to tell it where to go, whether you want to do all that sampling for some of the plotting or not. We're not going to because it's pretty slow. We have pretty nice plots in petitRADTRANS, we think, so we'll just use our plot style. You can turn that off and it'll just use the default matplotlib stuff. And whether you want to use PyMultinest or UltraNest, in this case, we want PyMultinest because we spent a lot of time figuring out how to install that on Colab. And then all you need to do is call the run function. You can pass it some various parameters that you would usually pass to PyMultinest or UltraNest. So how many live points you have, whether you want a constant efficiency mode, or importantly, whether you want to resume an existing retrieval if it's going on for a very long time, or if you want to start again from scratch. And so that would just be false. And then it'll run. I'm not going to actually run this because I've already done it. But in the end, it just tells you all of your parameter values together with the standard deviations on them. And then from here, you can start to generate all of the plots. If you do, I'd highly recommend trying to do this yourself, and especially going through and changing your model a little bit and rerunning the retrieval to see what kind of a fit you can get. This one only really takes, I think, about 5 to 10 minutes on Colab to run, so it's really quick to actually play around and get some idea of how to actually run a retrieval and how changing some of these parameters will actually affect the retrieval. And just a bit of a note on what I would recommend for standard parameters. For live points, most of the time I'd say 400 is probably good. 200 here is just to speed things up a bit. Some of our more complicated retrievals, we've ended up using 4,000 live points to just get a better sampling of your prior space. It's hard to really decide on what you need until you've actually run the retrieval and seen what your posteriors and stuff look like. But 400 is generally a good place to start. All right. So here is just in case you don't want to actually run the retrieval, you can just run this and it will get the output files for us. So then we can start making all of your kind of standard output plots for a retrieval. We have a function that just automatically generates all of these and sends them to a file for you, but I want to kind of go through them one by one so that we can actually see what they look like and understand why we're interested in them. So the first thing we want to do is actually just read in those output files from PyMultinest, which, oh, that's because I didn't run this. And it might actually rerun the retrieval now. Yeah. Here's an important note that I should have mentioned. Glad I ran this. The first time you run a retrieval, if you have set your model resolution, so you will be binning down the correlated k-tables to a lower resolution, the retrieval will stop after you have bin this. That's because to bin them down, it can only run on a single core, whereas typically you want to be running a retrieval on many cores or on a cluster or something like that. But once you've binned it down once, it's saved in petitRADTRANS, and you can just restart it, and everything should run smoothly. So you can see right now that it's actually binning that down, but I don't really want it to. Unfortunately, I think I have to wait for that now. That's fine. That is not fine. It'll go quickly here. Anyways, I'll carry on. So the first thing we're going to want to do is actually read in the output files that are generated from PyMultinest. With the getSamples function in the retrieval class, it will actually return a dictionary. So you can read in multiple retrievals so that you can plot multiple retrievals one on top of the other. And the keys in the dictionaries will just be those names, the retrievals that we set up way above. How is this not defined? It's right there. I'm sorry, this should have worked the first time. Oh no. Okay, I think I have all the plots saved over here anyway, so I'll just change to a different screen and can start showing those. Hang on a second. Apologize, I thought that this should work right off the bat. All right. So the first thing you're going to want to look at, though, is your best fit spectrum. So we have this plot spectra function that takes in a set of samples. So this is the samples that are output by PyMultinest and the names of the parameters. So both of these you just read in up here and are associated with that particular retrieval name. It returns the actual matplotlib figures and axis if you want to actually play around with them, or it'll just automatically save. But as you can see from this retrieval, it fits rather well. Unsurprisingly, we knew what this planet was. It had a fairly simple model, but you can see the spectra, and you can see the residuals in the spectra. If you have more data sets, it will automatically plot all of them, and it will show the best fit model extending out to whatever wavelength coverage you're interested in. I'm just going to try to make sure that, does this work? No, it's not going to work, is it? Hopefully this works when you all run it yourself. And I guess I will have to let the remainder of the two plots actually be the exercise, but I'll still explain what they are. And it's fine because they're basically some of the same plots that are generated by Eleonora. So the next one is going to be our pressure temperature profile. Actually, I think these are here. Aha. So you have a pressure temperature profile. In this case, it's just an isothermal profile, and it gives you the confidence intervals associated with this. So this planet looks to be around 700 Kelvin from this retrieval. And finally, the last thing we're interested in most of the time is going to be the corner plot. So this is the posterior distributions of all of the parameters of interest, and we can actually see what our temperature is, what our chemical abundances are, whether we've constrained them or whether it's more of an upper limit or unconstrained at all, as we see with CO2 and CO in this one. In the collab, it's only the water and methane. And once you have all of these plots, you're pretty much done with what we can do. After that point, it's up to actually interpreting the results. Do these make physical sense? What happens when you try different models and compare them? But yeah, that's essentially it. There's a few questions left in the lecture that might make for some interesting discussion on Slack. If you have ideas about how retrievals can be improved, or whether some of these methods make sense. Do these assumptions that we're making necessarily make sense, or when do they start to break down on us, particularly assumptions about 1D models or isothermal models? So these are really important things to think about when you're actually setting up your retrieval and understanding whether the results make sense. But that is everything you need to know if you want to run a retrieval in petitRADTRANS. There's a lot more detail to a lot of these functions that's documented on the webpage. And if you're really interested in running these, I highly recommend actually looking at the code to see what additional arguments and stuff are available and how everything works. All right, any questions?
Yes, there are two questions by Hossein. The first is, can you improve your retrieval by adding more free parameters? Yeah, and the second is, did you compare petitRADTRANS with other tools for creating models?
So I'll start with the second one. petitRADTRANS has definitely been benchmarked and compared to other models, and other people have used it as a comparison. I have not done that myself, so I can't talk about that, but certainly other people will have a better sense of how well it compares. It seems to do quite a good job. For the first one, simply adding more parameters isn't always a good idea. Of course, if you add more parameters, you can pretty much always get a better fit, but the question is adding more parameters justified given the data? So here's one area where using the nested sampling, PyMultiNest or something, is very useful in that it actually gives you the Bayesian evidence out. And so you can then start to do a Bayes factor analysis of seeing if I'm adding these parameters, does my evidence actually improve enough to justify the inclusion of the additional parameters? If you have very few data points and with large error bars, it's not really going to be justified to have a very high dimensional model. But if you have exceptional data quality and high resolution spectra and broad wavelength coverage, and you know it's as good as it'll ever get, then sure, throw as many parameters as you want at it. But then again, you run into the question, do you want to let the retrieval be very free and to constrain parameters individually, or do you want it to be more driven by physics and have kind of that built into your model? And those are open questions, I guess.
Okay, so I don't see more questions in the chat. Okay, so maybe we can finish here. And I think Giri wants to announce.
I have one more thing. Hello, everyone. We thought it would be a neat idea to take a group picture on Zoom. So I would kindly ask if...
Sorry, before we do that, there is one more question from Eva Maria.
Sorry.
It appeared now. Okay. Yeah, let me check. I've been going through your notebook at the same time and everything worked perfectly except for the PT plot in the end, which is completely empty. Any idea why? Best fit, yeah, and that's all. It seems that the best fit spectrum and the corner plot look fine. Only the PT plot, it's not.
I did something to break it on mine when I was running it here, so I'd have to rerun everything and take another look. It was working before when I originally sent it out, so I'd have to see if I've accidentally broken something. Sorry.
Yeah, actually, that the same happens to me, but at the same time, I have the corner plot. If you wanted to comment on that, I don't know if you need it. Otherwise, this one that you're showing right now, it looks also fine. Whatever you prefer. Evert?
I was there a question there, Eleonora?
No, if you want to talk about what you would have gotten in the collab, I managed to run it if you want to, but
yeah, sure. If you can show that, the results should look quite similar to what I'm showing on my screen here.
Yeah, it's the. I mean, in my case, I also don't see the PT profile, but I see the corner plot. If you wanted to say some more about the corner plot, otherwise it's okay.
I didn't have anything in particular to add to corner plot.
Just wanted to mention that. Cool.
If there are no further questions, then as I was mentioning, if everybody can turn on their cameras and we would take a group picture. And now it got switched to gallery. Okay, I got it. So once everybody turn on their camera, I will take a screenshot. We can wait 10 more seconds to give everyone a chance. So in 3, and then everybody can smile. So 1, 2, 3. All right, thank you, everyone. And yeah.
If anybody has any more questions about petitRADTRANS, feel free to put it in the Slack, and Eleonora and I will be happy to help out.
Yes, and we see each other at 4.